In this video, what I'm going to do is I'm going to show you an animation of how gradient descent compares to gradient descent with momentum in 2 dimensions. And then I'm going to show you the code for how to actually construct this. So we'll create it together. But firstly, I'll show you the animation. What we're going to do is firstly, we're going to look at gradient descent. And this is going to be a plot of x squared. So we have the function x squared, and actually what I'm going to do is I'm just going to plot the function for you so you'll see it beforehand. Yep, there we go. Alright, here is the function, x squared. It looks as typical, it's just a parabola. And now we're going to perform gradient descent to see how the minimum is found, which obviously the minimum is at 0, 0 here. We can just spot it on the graph. Let's start at x is -8. And what do we want to do? Let's put pause of 0.8. Alright, so we're starting at the point x is equal to -8. What have I done? I didn't plot enough points on the initial graph. There you go. So the purple point is at x is equal to -8. 1 step of gradient descent, 2 steps, 3 steps, 4 steps, and so on. Yeah, you can see that it converges to 0, and then it'll start to slow down. There we go. So it's pretty much reached 0 over there. Well, obviously, it starts to slow down now because the gradient is a lot slower. Now, what's that? That is with a learning rate of 0.1. And now let's look at gradient descent with momentum, and we're going to do let's put 20 points as well. We're going to do a lambda of 0.1, which is the learning rate, and then a beta of 0.9. Now, I know that there's different equations for gradient descent with momentum. I'm using this one here, which I'll go over in the coding section. But I've tried different equations that I've put it in. Sometimes you don't write the 1 minus beta. I've seen that before. And then lambda sometimes is only multiplied by grad x. I've also seen that before, but I prefer this one. Anyways, let's look at the graph. I'm just making sure that everything here is okay. We need to look at gradient descent with momentum. Alright, let's look at gradient descent with momentum here. Okay, so you can see that it starts off slow at first, and I'll explain why that is after you see this animation. Yeah, so it overshoots at the end. That's the point of gradient descent with momentum. I'm not sure if we have enough iterations, but if we do, then it'll also come back down to 0. So it's kind of like a bowl rolling down a hill. Like, people explain gradient descent like that, but this is a more true example. So it starts off there, and then goes up, and then it'll go back down again, then up, and it'll settle at this minimum over here. Alright, so the reason that it starts off slow is because we've set a beta of 0.9, and 1 minus beta is being multiplied by grad x, which is the derivative. So that's the term that's in gradient descent. So now it's only 0.1, or what is it? 1 minus 0.9, which is 0.1, and then lambda is being multiplied by that. This term here that we're subtracting in is less for the first situation because because 1 minus beta is being multiplied by it. So in gradient descent, it's only lambda that's being multiplied by it. But here we have lambda and then 1 minus beta. And of course, in the first iteration, v is 0. So we don't have any term added here. The reason that it overshoots at the end is because we still have that momentum term. This is the part where we talk about momentum. This is the term that's in reference to that. Because we actually keep information from the previous state, which is essentially this v, we're keeping the information from the previous state, and we're not only using the information from the derivative, we're using the information from the previous state. And that's why when it gets to the end, it overshoots because it still has that little bit of momentum from the previous steps, as opposed to gradient descent, just normal gradient descent, which doesn't overshoot because it only contains information from the gradient, from the current slope, which obviously is very close to zero when you get to that, that minimum. Now, I'm going to show you an example where you can see a far more useful case. All right, I'm going to just plot the graph first. Okay. This is the graph. If we start here, let's say that we start here, we go down here. Now you'd imagine gradient descent will just stop over here because there's no momentum to carry it forward. But we can get gradient descent with momentum to use the momentum to skip this local minimum and get down to the global minimum. Now you can imagine that this would be a potential loss function or something similar to it in a real life scenario. So you don't want to get to a local minimum. You want to get to something that's potentially a global minimum, but you want to get to the lowest possible minimum that you can get. And I'm going to demonstrate here that gradient descent with momentum can bypass this this minimum over here. What have I done? All right. Now we're going to have to work through a few parameters, hyperparameters here, because I don't remember the exact ones, but let's try gradient descent 0.01. Let's try 50 points, for example, and we'll do 0.3 just so you can see it a bit faster, and that should be fine. We'll start it. We're starting at 0.2 now. All right, let's look at gradient descent. Okay. Okay, so the learning rate is quite high, so you can see that it got down very quickly. But imagine a lower learning rate, so we just lower it slightly. Actually, I will do that. 0.0, I don't know, 008. Okay. Okay. Essentially, it's starting off a bit higher. So if you want, you can keep lowering the learning rate, and then it'll go around here. But anyways, point is that gradient descent makes it stop over here in this little local minimum. Now, what you could potentially do is you could play around with the learning rate so that the first iteration, so instead of going to here, it would go over to here, for example, and then it would go down to this minimum down here. But it's a bit tedious to do that, and in a scenario where you don't have access to this graph, you wouldn't be able to really see what you need to do. I mean, you could play around with it, and that's useful definitely in neural network sense. You have to mess around with the learning rate because who knows what the graph looks like in a real life scenario. But all right, let's try lambda exactly the same, 0.008. Pause there. Okay, don't worry about me changing these parameters if you don't understand that, because I'll go over the code and we'll code it together from the start. But all right, let me check this. All right, let's try a beta of 0.9, a lambda of 0.008, and we will try 50. 50 iterations, that is. Gradient descent with momentum. Oh, I just realized I forgot to change the function. So gradient descent with momentum with the same parameters I just changed. Okay, this is with momentum. There you go. So you can see it overshoots it, which is good in our case. And all right, it won't get there because we haven't had enough iterations. Maybe not. So it won't get there because it didn't quite overshoot, actually. So it wasn't because of the amount of iterations. It didn't quite overshoot, which means that we could potentially increase the learning rate slightly. Let's try 0.01. But you can also play around with this beta parameter as well, but it's easier just to change the learning rate. All right, so you can see that, yeah, it overshoots, which is good in our case, and it starts to pick up speed again. It starts to pick up momentum. And there you go, it'll start to go there. Do we have enough iterations? We don't have enough iterations. Now the iterations are finished. Let's do 100 and we'll pause for a very slow amount of time. It's lagging a bit, I think. Yeah, it comes up slightly and then it'll slow down and go back down again. And you can see like it's building up over here, which shows that it's going back here. You can't really see it but you can see it's getting thicker. Okay, that is the animation part. Let's go to the coding part. All right, now we're going to start coding everything you basically saw in the last section, which is going to be gradient descent and gradient descent with momentum. We can start by importing the libraries that we'll need, so NumPy and Matplotlib. As PLT. There we go. Firstly, we're going to define the functions, and I'll just define the function right now for x squared, and by functions I mean the actual equations, the mathematical functions. That way you can change it up however you like. Let's define, we'll call it f, we'll just call it f, and it returns x squared in this case. Then we need one for the derivative as well, because we're going to be calculating the gradient, which is essentially the derivative. Now remember, this is going to be only for the 2-dimensional case, and I'll likely make videos on 3-dimensional and potentially any case later on as well. So let's call this let's call it df, and the derivative of x squared is 2x. Okay. All right, now we're going to create a function for gradient descent. We'll start with that one. So we'll call this gradient descent. And what will it take in? It will take in an initial point, which is, we'll just call it x initial. And we'll define x initial up here. Let's say a -8. I think that was on the last one that I showed you. All right. What do we need to do? We need to first plot just x squared, because when we actually show the animation, the points are going to be on the line, so we want to make sure that it's actually on the line. How are we going to do that? We'll define a, say, plt.plot, so we'll just plot it straight away. We need linspace, which basically returns an array of points between some values, so between -10, 10, and it returns 1000 points, let's say. Let's put 1001, because I think that works out to be better. And then we need to take the function of that, so we can just pass it in directly, np.linspace, -10, 10, 1000. So all this will do is it will create an array of all the x points and an array of all the y points, which is f applied to that function, which is going to be x squared. And this is going to be from -10 to 10. And we will create the color of it. And if you don't know how to do the color, it's just C, you put C. And then you can Google the different colors out there and what they're specified by. But a C like that in speech marks, that's cyan. And I like that color, so we'll keep that. Then what do we need to do? We need to add the points, that gradient descent. Well, we can do the algorithm first. Let's do the algorithm, and then we can worry about the plotting later. So, well, one, I will write plt.pause. And we'll pause for 1 second. That just makes it pause so that the animation can take place. You can't use time.sleep. That doesn't work with matplotlib animations. You have to do plt.pause. Alright, so for I in range, let's say 20 iterations. Firstly, we calculate the gradient, which is, because we're going to use this formula here, x is equal to x minus lambda, or learning rate, times the derivative, or grad x. Now, grad x will just be df of x. So this is just this function applied to x. That's going to be the gradient. And we actually need to define x. So x will originally be x initial. We also want to plot the initial point. So plt.scatter, that way we can add points on the actual graph, and they'll appear like the points that you saw in the last section. So plt.scatter will go x initial and then f of x initial. And what they'll do is they'll just plot the initial points. So x initial, that's -8, that's going to be the initial point, and then we're going to apply x initial squared, which is going to be 64, and that's what it's going to apply at first. And we'll put this color as M, which is magenta. Alright, so I'm kind of going all over the place here, but this section here, that's just plotting the original graph and then the scatter, which is the point. So this is going to be plotting x squared for -10 to 10, and this is just the point x initial, f of x initial. Then we want to change x. So the first point is x initial, so we just set it to that. And then x is equal to x minus lambda times grad x. That's the formula for updating for gradient descent. Yeah, so we specify a learning rate, which is lambda. There's different Greek letters that are sometimes used for it. I prefer lambda, so we'll just put 0.01 for now. So now we specified lambda, multiplied by grad x. That's the new x. And now what do we plot? We plot a scatter plot, which is just the point. So we're just plotting the individual point here. That's how to make an animation. I'm not sure if you can make an animation with a list. I suppose you can, because you can append it to the list, and then you have a list of all the points, and then you create a for loop within that list, and that makes the animation. If that didn't make sense to you, don't worry. That's just me thinking out loud. But we'll do it this way. So if you do want a list of all the points, you can obviously just append it to the list as you go. We'll just keep it like this. So we have x, which is just the x point. And the first iteration that we're plotting here is going to be the first update. And that's why we're plotting initial points over here, because we want to plot the initial points and then we plot the update. This should be over here. And we'll put 1.5. All right, so we plot x and then f of x, and we'll put that as magenta as well. Now, I'm looking at it, and this actually might be everything that we need to do. Is that really all there is to gradient descent in 2D? I'm trying to remember. I think it is. Let's try it out. So gradient descent and x initial. Oh, of course, we need to pause it. Pause 0.5. Let's run. Yeah, I've realized what I've done. I wrote 10,001 there. Hey, it works. We specified a small learning rate, but it works. Let's just try a bigger learning rate here so you can see it doing something. Great. And what does it do? It doesn't overshoot because there's no momentum. It just slows down because the gradient here is pretty much 0, and we're taking it ran out. I don't know why it closed, but you saw what it was doing anyways. let's get to gradient descent with momentum. We'll just this here. Okay, gradient descent. Okay, we're going to have to specify a beta term here now. And I'm assuming you know the equation for gradient descent with momentum. You can just Google it if you don't, but I'll write it down. You'll see it over here. Specify lambda is 0.1, and then beta, which is the momentum constant. That's typically what I've seen to be 0.9, so I'm going to do 0.9. Alright, so we're going to plot... Firstly, we're going to actually plot the same thing, so we can just copy this from before. Now we still need the scatter plot and then the pause. So this is exactly the same as the previous one. And you could functionalize this as well if you wanted to, but that's pretty straightforward, so I won't do that in this video. X is X initial, and then the only difference is going to be this loop here. Let's run both of these for 50. All right, we still calculate grad X, and that's df of X, but now we update it differently. And the update is V. We need to calculate this momentum, this new term V, which includes the momentum. So that's beta times the old value of B plus 1 minus beta times grad X. Now there's different equations for it. I have seen this one, and I've seen it without this one. I've also seen lambda only being multiplied by one of them, and then, well, then in that case, what you do is x minus v. I think I've seen like a bunch of different ones. I don't know why. Honestly, there's so many different ones, but this one makes more sense to me. So we're going to do it like this: grad x, and then the update is just x is equal to x minus lambda times v. I believe that's right. V is beta v, 1 minus beta times grad x. Yeah, that looks right. And we need to initialize the initial term for v, which is just 0. And that is the entirety of it. Let's plot it. So we plot, I know it's plot over here. X, f of x is, yeah, that's the entirety of it. And for completeness, I actually probably should figure out why we write this plt.show, but I've always just written it. And I've always seen it in code. So anyways, plt.show. So what we're doing, essentially we're initializing, well, this is the first value here. We're setting v to 0, which is the first value of v. And then for 50 iterations, we perform gradient descent with momentum. Start by calculating gradients, which is df dx, and then calculate v. And then the new update is x is equal to x minus lambda times v. Then we scatter it, which is the point. So each of these iterations will scatter 1 point. And then we pause for a bit so that the animation can run. Let's run it. Wow, it is very slow right now. Oh, that's funny. Like that. It was in the function before. I'm sure you noticed that, but when I wrote gradient descent with momentum, it was in the function. So yeah, you can see that it starts off slow because there's no momentum built up. It's like letting a ball just drop without pushing it at first, and then it builds up, build up speed, and then yeah, it goes back down again, and it will settle down in this point here. You can see that it's not very useful for this sort of shape, but you know, imagine what a real life loss graph looks like. You know, so there's probably so many different local minimums there, or minima, that momentum would be useful to get past those points. that is how to code momentum. From what I know, momentum is useful in the sense that, like, aside from the case that it can let you pass local minimum, it also takes less steps to converge. Now, I don't have a demonstration with you for that, but if you look up a lot of videos on momentum, they show that zigzag pattern that gradient descent typically takes and that momentum avoids. So in that sense, it will smooth out that zigzag pattern and it will converge in a lot less time. If that doesn't make sense to you, don't worry about it. If you're interested, just search up videos on momentum. There's a little bit out there. So if you type in gradient descent with momentum, then there'll be videos out there and they'll show that zigzag pattern. Anyways, that is gradient descent with momentum and how to code it in Python. Again, that was for the 2D case, and get excited for a video on a 3D case. Thanks for watching.